everyone. Thank you for coming today, and thank you for Voxel 51 and the Union AI. So my name is Chongjin, and currently I'm a third-year PhD student from the Department of Industrial and Systems Engineering at the University of Washington. And my PhD advisor is Professor Shuai Huang. And currently I'm also an Amazon AI PhD fellow. So today I'm gonna talk about one of our work called ALOM, automated MLLM-based anomaly detection in complex environment monitoring with uncertainty quantification. So first of all, I want to thank all of my collaborators from the University of Washington and the WISE company, including Ryan, Xinyi, Professor Shuai Huang, Professor Chaoyue Zhao, Dr. Pei Guo, Dr. Wei Li, and Dr. Lin Chen. And here is the outline for today. So I will begin with the introduction. There are many real-world cases in video anomaly detections. So here I want to take the smart home monitoring as an example. So if you buy a smart home cameras in the market and you can install the cameras at your home, then you can also download the app, download the mobile app in your smartphones. So we want to let the app to send the notifications to users when the app find any anomalies in the smart home videos. So that means that the app needs to keep monitoring the videos they recorded. So here, for example, some normal videos include like a peaceful home and a dog just walking around at your home. But they also have some very obvious anomalies, including forced entry and a baby falling off a bed. Thanks to the development of large language model, especially multi-modal large language model, and here we can use the MLLM method to do the VAD, the video anomaly detections. So one of the very obvious advantage of MLLM is that the MLLM can provide real-time predictions compared with other traditional machine learning or deep learning VAD methods. And also the MLLM can provide very detailed reasoning behind the anomalies so that it can improve our users' trust in the predicted anomaly labels. So for example, here, we can give the same videos as what we mentioned before to multimodal large language models. And here is the prompt. So we ask MLLM such as ChatGPT, Gemini, or Claude to identify potentially anomalous situations. And also, we ask the MLLM to provide video descriptions, the reasoning behind the anomalies, and the labels, which is normal or abnormal here. So in this case, the MLLM can successfully predict the anomalies. It can find that in these videos, there is a man pushing a window. And the reason the LLM thinks this video is abnormal is that this video involves a potential break-in or other illicit activities. So here, the MLLM can say that this video is abnormal. However, there still exist some challenges in MLLM-based VADs. So for example, here, this is videos. The MLLM finds that the videos includes a cat perching on the railing of a porch, and this environment seems very peaceful. However, there are two potential kinds of reasoning behind these videos. So one is that the MLLM thinks the cat is very relaxed, and the video seems very calm and ordinary. However, another reasoning is that the MLLM thinks the pets may be escaped from the home, which should be considered as anomalies. So these two kinds of reasoning can lead to two labels. So should these videos considered as normal or abnormals? So there are the challenges in the MLLM-based VAD, which is the contextual ambiguity. So here we provide a solution for that, which is MLLMs with uncertainty quantifications. The MLLMs can provide very detailed context explanations thanks to its large number of training data and a very broad knowledge, very broad word knowledge. And for the ambiguity challenges, we need to quantify its uncertainties behind the ambiguity in a statistical way. Now I will introduce our detailed methodology. So our framework is called ALOM. Here we take the data as the input. This data can be videos, images, text, or Tableau data. In today's talk, I will take the videos as an example. So for each videos, we will give them to different LLMs, and each video will go through the same LLM reasoning chains from different LLMs. And after the reasoning chains, the LLMs can give different decisions for different videos. And based on the outputs and the results from the LLM reasoning chain, we can quantify the uncertainties behind each data. And then we will give the video. We will let humans to make the final decisions on the video with high uncertainty, and we will give the LLMs to make the final decisions on the videos with low uncertainty. Then a question comes up. So how should we? So how to quantify our uncertainties here? We proposed a method. Which is called LLM reasoning chain, which consists of 3 stages. So in the first stage, it's called data comprehension. In this stage, we will give the LLM the video data and let the LLM provide the video descriptions on this data. Then we will give the video descriptions to the second LLM and let it provide the analytical thinking, which is generate the reasoning behind the decisions, like why do you think this video is normal, or why do you think this video is abnormal? And then based on the reasoning, the LLM will generate a hypothesis. Here, the hypothesis means the initial predictions. In our case, it's a binary label, which is normal or abnormal. And for some data sets, for example, in our smart home data set, there exists some side informations. In our case, we will give the large language model some anomaly rules, like what kind of videos should be considered as anomaly, and what kind of videos should be considered as normal videos. After having this side information and the reasoning and also the initial hypothesis, the large language model will proceed to the reflection stage. It will reflect on its initial hypothesis and generate the final decisions. So here we express this LLM reasoning chains in a probabilistic way, which is shown here in these formulations. So we want to calculate the probability of the final decisions H given the data and the detailed task instructions. And this probability includes three probability distribution considerations, which is from these 3 stages. So our ALOM framework has already been accepted by Inform's Journal on Data Science, and all the details are provided in our paper. And as I mentioned, our framework includes selective decision-making techniques. So here we provide an example of LLM reasoning chain. And after calculate the final integrated uncertainty score S, we can rank our video data based on the UQ scores from low to high. And then we will give humans the data with p% highest UQ scores, and let the human to make the final decisions on these p% videos. And we will let the MLLMs to make the final decisions for the remaining videos. The reason why we designed this combination is that we want to not only improve the detection accuracy, but also save our costs. So typically, we think that human can provide the detections with high accuracies, but it also incurs many labor costs. Well, for the MLMs, typically it can save some labor costs, but its detection accuracy is not as high as humans. So we build this selective decision-making methods and use it to give our use it with our LLM reasoning chain. Then I will introduce the computational pipeline of the UQ scores. So for our UQ scores, it includes two components. One is the individual UQ score, and one is the optimal weights. After we calculate the individual UQ score from these three stages, we need to design the optimal weights to combine them as the final uncertainty score. So I will first introduce the calculation of individual UQ scores. The first stage is data comprehensions. So to calculate the S data, we begin with the data I. Let's say this is the data instance I. Then we will give this video data to different LLMs. Assume we have 3 different large language models. The 3 large language models will provide different data descriptions on the same data. And then we will calculate the pairwise cosine similarities behind these video descriptions. And after we get these cosine similarity vectors, we can build a similarity matrix here, W. In W, each row means each data in the training sets. And we will use the probabilistic matrix factorizations to reconstruct the similarity matrix based on the latent matrix U and V. So after we have V here, we can calculate the S data by solving these least square problems. Here, the W is the similarity vector for the test data instance. Then we proceed to the second stage, analytical thinking. So in the calculation of its task, we also use the probabilistic matrix factorizations. But the difference here is that we need to separate the uncertainty source. Here we have 3 uncertainty sources, which is uncertainty from the analytical thinking, uncertainty caused by the variability of data descriptions, and the LLM inherent uncertainties. So we derive a theorem here, and we can use this theorem to only consider the uncertainties behind the analytical thinking, which is the reasoning on the videos. And here is the final formulas for the S task. The first item is the expectations of the reconstruction errors on the matrix factorizations based on different H tilde. H tilde is a hypothesis. So, and the second item is the general reconstruction error. So we calculate its task based on their differences. This is our final stage in the LLM reasoning chain called reflection. To calculate the SREF here, as what I mentioned, we have some set informations for our smart home data sets. So here, this is an anomaly taxonomy in smart home, which is built based on our prior work called Smart Home Bench. In this set informations, it includes the definitions on the abnormal events and also the normal events, and also our anomaly rules. So after having the set information, the reasoning, and the hypothesis, we can embed them and use their embeddings as the predictors. And for our outcome labels, we define y-adjust here. So when the large language model adjusts their hypothesis in the reflection stage, then y-adjust should be equal to 1. Otherwise, it is 0. We will build a logistic regression model based on these 3 predictors and these outcome labels. And we calculate the probability of y-adjust equal to 1 based on the results from different LLMs. So we split the reasoning. So we split the LLM reasoning process into 3 stages. Is that our cases is very complex. As I mentioned, the video anomaly detections include a lot of ambiguities. So for large language models, it's very hard for them to correctly detect the ambiguities. So we split these complex tasks into 3 small subtasks so that large language models can better follow the task instructions in each stage instead of just give one large language model a very long prompt like a chain of thought. If we give LLM a very long prompt, it may make them get lost. And now after we calculate the 3 individual UQ scores, we can get the optimal weights alpha for a given P to combine them. So here, we calculate our optimal weights by maximize the detection accuracies. And to enhance the reliability of the optimizations and also avoid the noise from the data set, we calculate the alpha based on the average of we calculate the alphas by maximizing the average of k-folds of detection accuracy. So notably, the detection accuracy here depends on the P, which is the rejection rate of large language model, and dk, which is the k-folds data. And also, we will calculate the alpha based on a grid search on the alpha values. So here are our experiment results. We begin with an overall evaluations. So in our paper, we include 2 kinds of baselines. One is the prompting baselines without UQ methods, and the other baselines includes the UQ consideration here. So we evaluate along on different performance metrics, including overall accuracy, recall, F1 scores, and accuracy on de-ambiguity. Here, de-ambiguity means the data set which includes ambiguities. And we can see our alarm can achieve the best performance in all of these performance metrics. And for these very complex videos, the alarm can achieve 71% accuracy. While for some advanced prompting methods, like chain of thought, it can only achieve 44% accuracy. We also evaluate our the effectiveness of our well-designed UQ score. So here we include the baseline called the random drop, which means we randomly dropped the P% videos from the LLM decision makings and let human to make the final decisions on these random P% videos. And we can see that our alarm can achieve higher ratio of detected misclassifications in the rejected cases in all these rejection rate P. And also we evaluate the impact of rejection rate P. So here we include the final integrated scores S and the 3 individual UQ scores, the S task, S data, and the S ref. And also the random drop here serve as a baseline. So our final integrated score S can achieve the highest overall accuracy among most of P here. And also we evaluate the impact of the MLLM ensemble designs. So for example, in figure A, we can see the x-axis is the number of MLLMs, M. And if we increase the M size from 2 to 5, the overall accuracy also increases, which means that more LLMs here can lead to higher overall accuracies. And also we evaluate the mean marginal accuracy gains of different large language models. Here, based on these results, we can find that in the same large language model families, like GPT-4o versus GPT-4o mini and Gemini 1.5 Pro versus Gemini 1.5 Flash, if these LLMs are in the same families, then the models with larger parameter size can achieve better marginal accuracy gains. And we also extend our applications into wound image classifications. So these results here have very similar trends as in the smart home monitoring. And let me conclude today's talks. So based on today's talk, we can see that by incorporating UQ with selective decision makings, alarm can improve performance in ambiguous situations. And also, our alarm decomposes the decision-making process into 3 stages, which can enable more accurate and fine-grained uncertainty estimations, as shown in the comparisons with the random drop baseline. And also, we proposed some future work directions. So our alarm can be optimized by refining LLM ensemble compositions. Like for examples, we can design which kind of LLMs should we included in the LLM reasoning chains. And also, we can incorporate additional modalities. So in today's talk, I showed the results of the smart home monitoring on the video anomaly detections and also the wound image classifications. But we also think that our alarm can be extended to the tabular data and the text data, since the 3-stage LLM reasoning chains is very similar to the human's decision-making cognitive trends. And also, we can use transfer learning on the alarm framework so that we can apply alarm to other domains. And thank you for listening today. And also I want to thank you all my collaborators from University of Washington and the WISE companies.